All right, last class we were talking about definite integral, and this notation now with the little a and the little b, those are your bounds of integration. And the lower bound, if it's smaller than the upper bound, then that means you're moving from left to right, and it would be positive unless it's below the x-axis. And total signed area, of course, then you're talking about the area above the x-axis is positive and the area below the x-axis is negative. So we were doing it with geometric shapes. So the question today is, what if the area does not form a familiar geometric shape? So let's say that we had something like this. Okay, we got a curve, and we want to go from A to B. I don't know if you guys remember on the first day of school, I think I showed you a video that was brain pop. That was called What is Calculus? Davis remembers.
I remember.
Just say you remember. But this concept we're about to talk about was mentioned in the brain pop video. So one way when mathematicians, and by the way, the calculus that we're doing today is only about 200 years old. So it's quite young in the history of mathematics, relatively speaking. Like think about the Pythagorean theorem. That was from like 300 BC. And we're doing mathematics that was only created about 200 years ago. So it's very young. So what the mathematicians did at the time is they said, well, I don't know how to find that exact area, but what if I were just to use some rectangles? I can find the area of the rectangles, right? Now, with the area of the rectangles, would that be more or less than the actual area under the curve?
Less.
Yeah, it would be less because you can see there's a gap up there. Or we can use more rectangles. And I heard Christopher say you could use rectangles and triangles, right? Which are trapezoids. We'll talk about trapezoids later. Or we can use even more rectangles, okay? So there was this mathematician, Bernard Riemann. How old do you think he looks in that photo?
But he's like 20.
In the old days, he's probably like 32.
Well, he died when he was 39, so we know he was younger than 39 when this photo was taken.
I'm going 25.
I want to put in there, Ben.
Y'all seen that
I said 22.
25.
I don't know when the photo was taken, but obviously he was younger than 39. But he looks much older, doesn't he?
Well,
Looks like he's like 55.
Actually, I'm feeling like
Alex, what do you guess?
30. Just 30. That was on his 30th birthday. That was his birthday present.
Alex, what do you guess?
Let's move on, shall we? So this guy, Bernard Riemann, he figured out that the technique that you want to use is you want to find rectangles that are equally spaced. Because like what we saw here in these photos, like these rectangles, if they were all equally spaced, but you don't have to do equally spaced, right? You could find a really skinny rectangle and a really fat rectangle and add them all up. But if you found all of them, if they were equidistant from each other or equally spaced out, then you'd have more of a systematic way of finding them. So right now, there's going to be two ways of doing this. The left-hand evaluation points, also known as a left-hand rule, and then there's a right-hand rule. So I want you to look at these pictures here. I think I gave you this slide in your notes.
Yes, you did.
So do you see that you've got in both diagrams, we have 4 rectangles, and they're supposed to be, even if it's not drawn perfectly, they're supposed to be equally, have the same width, right? Do you see how in rectangle number 1 for the left-hand rule, the height of that rectangle is the left bound of that particular rectangle? So for this rectangle, you've got the left and you've got the right. And if we go to the left and go up to the curve, that's the height of that rectangle. Same thing for the second rectangle. We go to the left of it, the left side of it, and then we go up until we meet the curve, and that's the height of that rectangle. And for the third, and then again for the fourth. Whereas over here, on the right-hand side, for the right-hand rule, we've got 4 rectangles, but to find the height of it, we're actually going to the right side of the rectangle and up to the curve and then over. See the difference? Mm-hmm. So we're going to be talking about, sometimes we're going to be evaluating Riemann sums, is what this is called, when we're using rectangles, either using a left-hand rule or a right-hand rule. So sometimes it's a challenge to recognize the right hand versus the left hand. So over here, I want you to take a few moments to yourself and determine which one of these diagrams would be using the right evaluation points and which ones would be using the left. All right, so that one on part A, that's the right. So again, if you look at one of the rectangles, the height of that rectangle is where the right side of that rectangle meets the curve. And the same thing with the second rectangle. So they all have to be the same. You can't do a mixture of right and left. But then over here, that's a left. So if you look at this first rectangle, the height of that rectangle corresponds to the left side of the rectangle intersecting with the curve. Okay, and then part C was left again, and then part D was right. What about this one?
Either.
What do we call the middle?
D
The mid,
Midpoint.
the midpoint. So this is a trick question because it's actually not right or left. It is the midpoint. So if you look at the rectangle, this first one is from -3 to -2, and they found the midpoint and went up and met the curve, and then they went across. So you could use, there is something that's called the midpoint rule for Riemann sums. We are not going to be doing that in this class, but there is such a thing. So like the AP calculus class, they use right-hand rule, left-hand rule, midpoint rule, and then later we are also going to learn the trapezoidal rule. So we're going to start by taking a few baby steps before we get into the Riemann sums. So we're going to look at number 1. All right, so we're going to look at number 1. We want to approximate the area bounded by this curve, the square root of x, from 1 to 4, and we're going to use left evaluation points and 3 rectangles. So what we're going to want to do is sketch a picture of the curve y equals the square root of x. What does that graph look like? Y equals the square root of x. Nope. All lines are straight.
Problem.
Nope. It does go like that, Annika. Nice. It's going to be half of a sideways parabola. Okay, so I'm just going to draw, and I like to sort of exaggerate my pictures because we are going to be putting rectangles underneath it. So that will be the graph y equals the square root of x. If you weren't sure what the graph looked like, you have a very expensive graphing calculator where you can graph it. So we want to go from 1 to 4, and you just eyeball it. It doesn't have to be a perfect sketch, but maybe 1 is right here, and maybe 4 is right here. And we want to break it up into 3 rectangles. So I sort of divide my region from 1 to 4 into 3 rectangles. So how wide will each rectangle be?
1.
And how do you know that?
Because it's the difference. There's 3 spots, so it should be 3.
Right, so if you're looking at the width of the rectangle, the width, you're looking at the difference in your bounds. So that was 4 minus 1 divided by the 3 rectangles. And we'll talk more about that in a minute. So the width is 1. So once I have my vertical bounds where I know like this is 2 and that x value is 3, then I go back to my question. It says left evaluation points. So we have rectangle 1, rectangle 2, rectangle 3. So for the first rectangle, I'm going to go to the left of it, which is when x is equal to 1. I'm going to go up to where it intersects the curve, and I'm going to draw a horizontal line straight across. So that becomes the first rectangle. Same thing for the second rectangle. To the left of it would be when x is 2. Go up to where it meets the curve, and then draw a segment straight across, and then you make your second rectangle. And then same thing with your third rectangle. It could be nice if you had different colored pencils. You could make it look pretty. So sometimes I like to make a little, sort of organize a little chart here. So we're looking at our rectangles. We've got rectangle 1, rectangle 2, rectangle 3. The width for all of them is what? 1, 1, and 1. Let's talk about the height. I'm going to give you a minute to catch up here if you're copying down this table. Well, let's talk about the height. So when we go to our picture, the height of rectangle number 1, how are we going to find that height? Nope. Because this is the function y equals the square root of x. So this y coordinate, wouldn't that be the same as the height of the rectangle? Right? So the x coordinate is 1, and the y coordinate would be what? 1, because it's the square root of 1. So in other words, we're doing f of 1 for the height. So that's the square root of 1, so that's just 1. What about the height of the second rectangle?
It would just be the square root of 2.
It's the square root of 2, right? It's just going to be f of 2. So the square root of 2, which is just the square root of 2. We're going to use our calculators in a minute because we're going to get a decimal for our answer. And then for the third rectangle, what's the height? F of 3, square root of 3. Notice that we are not using f of 4. Okay? So that means that your area, pretty simple, right? It's only 3 rectangles. That's going to be about equal to each width times each height. So 1 times 1 plus 1 times the square root of 2 plus 1 times the square root of 3. Take a minute and calculate that. Yeah, I went to 3 decimal places. It didn't specify, but yeah, it is about 4.15 or 4.146. All right, let's do number 2. I'm going to see what you can do on your own. It's basically the same thing as number 1, except now you're using right evaluation points. All right, so the difference here is that you're using the right evaluation points. So the height of rectangle number 1 is going to be what?
2.
Nope.
Square root of 2.
Square root of 2. So this time it's going to be f of 2, which is the square root of 2. What about the height of the second rectangle? Yeah, f of 3, which is square root of 3. So we're using the right evaluation point. So once you divide up your rectangles like vertically, you have to go to the right of the first rectangle, go up until it meets the curve, and then go straight across. So that's the height of that first rectangle. So yeah, your area is going to be approximately 1 times the square root of 2 plus 1 times the square root of 3 plus 1 times 2, which is about 5.146 or 5.15. So you can see in the picture that the left evaluation points, is that going to be an overestimate or an underestimate of the actual area? Underestimate. And then the right evaluation points, is that going to be an overestimate or an underestimate? That's an over.
The difference.
Yeah, it does seem like you can maybe average them and get the actual area. And maybe in this particular case, that might help you because it's a relatively simple curve. But if your curve gets more complicated and you have a lot of turns to it, then that technique is not really a good one. And I was going to say, and then students will often say, well, wouldn't the midpoint give you a better estimation? What would actually give you a better estimation would be to use more rectangles. Right, because then you would have, especially the way that this is drawn up here, you'd have less of a gap there if you were to use very, very skinny rectangles. We'll talk more about that next week.
100.
Or to infinity.
Then,
Like take a limit. What? All right. So you should have noticed that when we were finding the area of these rectangles, right, we were doing the width times the height plus the width times the height plus the width times the height. Now, Riemann is the one that said, let's make all of our widths the same. So if we have an expression like this, like width times height 1 plus width times height 2 plus width times height 3, et cetera, don't they all have a common factor of W? So couldn't you factor out the W?
And yes.
And then you'd be left with what?
H1 plus H2 plus H3 plus plus Hn.
Plus H sub n. All right, let's talk again about the width. So yeah, this is actually the formal way that we would do a Riemann sum. This width, remember when we did it over here, the width was, you want to take your bounds and subtract them and then divide by the number of rectangles that you have, okay? So you may want to write this down. I don't know if I gave you space for it. Okay, so the width of each rectangle is equal to B minus A divided by N, where N is your number of rectangles, and A and B are your bounds of integration. So when I say, again, bounds of integration, remember when we were talking about definite integrals, it's kind of sloppy, talking about definite integrals, that was from A to B. So when I was doing this over here, what we were really doing is using a Riemann sum to estimate the integral from 1 to 4 of the square root of x dx. Okay, so the smaller number being your lower bound and the larger number being your upper bound. Okay, so that's where that B and the A come from. So let's take a look at number 3.
So,
Would you look at that? It's the exact same
what
function.
was 6 recs?
We're using 6 rectangles. You want some time?
Yeah.
All right, have a go. Yeah, this width of each rectangle, I should have mentioned it before, is known as delta x. Delta x. We'll talk more about that next week, the delta x. Delta meaning what?
Change in that.
Change. So it makes sense. It's your change in x because you're talking about how are your rectangles changing as you go horizontally. Just going to catch up here. What would be the height of your first rectangle?
1.
Because it would be f of 1, which is the square root of 1, because we're still in the square root function, which is 1. What about the height of the second rectangle?
Square root of 1.5.
Yeah, because we're looking at f of 1.5, so the square root of 1.5, whatever that is. Third rectangle,
2.
f of 2, square root of 2.
Wait, do
The
you
fourth.
write like f of all that, or can you just do the?
No, you don't. But when we get into like the trapezoidal rule after the quiz next week, then you'll see that it's useful. The next one, f of 2.5, so the square root of 2.5, and then f of
3.
square root of 3, and then finally f of 3.5. Now, be careful. Make sure that you're paying attention to this because you don't want to just go all willy-nilly and start doing f of 1 all the way out to f of 4 every half of an x. Because you're not using f of 4 because that's not the height of anything. Okay? When you're using the left evaluation point, you're not going to use the b value, just like when I did the right evaluation points, I didn't do f of 1 because that was the left side and I was doing right evaluation points. So make sure you're paying attention. Don't just do every single little value there. Pay attention to what the height of each individual rectangle would be. So instead of writing it like I did here, where I have width times height, we know that they all have the same width. So for the area, you can look at doing approximately 0.5 times the sum of 1 plus the square root of 1.5 plus the square root of 2, square root of 2.5, square root of 3, square root of 3.5. And I write this chart mostly to sort of help you organize your thinking process, but you don't have to write this chart if you want to jump right down here to this step. I would need to see one or the other. You guys listening? On the quiz, I want to see one or the other. Either the chart with your work organized like this, or this is how you might see like on an AP exam. The width times f of whatever plus f of whatever plus f of whatever. And then, of course, you can go to your calculator, which told you what? It's about...
Like 4.04, and then I also got 4.41.
It is 4.411.
Sorry.
That's interesting because we have to have the same function. First, we did 3 rectangles on left evaluation points, 4.146, and then we got right evaluation points, 3 rectangles, 5.416. Now I've got more rectangles, 4.411. We could do it again, right? We could do like 12 rectangles, and we probably get an even more accurate number that would represent the area under that curve. Do number 4 all by yourself, and then number 5, we're just going to talk about the width, and then we'll be done. So let's talk about the width. Sometimes I like to calculate the width, which is, of course, delta x, before I draw in my divisions of the rectangles. But you could probably figure it out pretty easily. So the width would be the upper bound minus the lower bound divided by the number of rectangles that you have, which is 4. So that's going to be 2 over 4, so it's a half. All right? So now I know that I'm going to go to... that's going to be 2, so that's going to be 1.5, and that's going to be 2.5 there. And I'm doing right evaluation point. So for the first rectangle, I go to the right, and I go straight across to make my rectangle. There's the first rectangle. So this is going to be an overestimate of the actual area, and then something like that. All right. So now, if you want to skip that chart, you can just say, okay, well, the area is going to be approximately 1/2 times f of what? Yeah, f of 1.5. Whatever that is, plus f of, plus f of, plus f of. So notice in this one, I'm not using the 1, that was my lower bound, but I am using the 3, the upper bound, because I'm doing the right-hand rule. So then we're looking at 1/2 times whatever 1.5 squared is, plus 2 squared, plus 2.5 squared, plus 3 squared, and you put all that in your calculator. Notice that the actual calculation is not complicated, right? There's nothing more than what you did in middle school, squaring, adding, but the concept is the calculus. So 10.75. So for the last one, I just want to talk about the width, which we're calling delta x. We're not actually going to, it just says how wide should the rectangles be. So again, it's just b minus a divided by n. So that's 2 minus 0 divided by 5, since that's 5 rectangles. So yeah, the width there would be 2/5. So you can see that in reality, some of this can get really tedious because then you'd be doing 2/5 times a bunch of values there.